Let's consider a problem involving friction. We'll have a hockey puck on ice and a large clear field of ice so that it can go a large distance before stopping, not going to run into anything. Let's suppose the mass of the hockey puck is 1.2 kilograms, that the coefficient of kinetic friction is about 0.25 between the puck and the ice. And let's hit the puck, give it an initial speed of 23 meters per second, and ask the question, how far will it go before coming to rest? There are really two aspects to this problem. We have to look at the friction force itself, which is causing the acceleration or deceleration, if you will, the puck beginning at the 23 meters per second and eventually coming to rest. And then we also have the actual motion of the puck. We'll have to take both of those into account. Let's start out by looking at the friction force. Let's suppose in the drawing, well, to the right is the positive. We're also just going to let the blue line of the coordinate system represent the ice itself. Let's suppose that the puck is moving to the right. The speed as it goes along doesn't really have a strong effect on the friction force. We're going to take the friction force to be constant. And as the puck is moving to the right, the friction force is going to oppose that motion. So the friction force is going to be to the left. And we also know the friction force depends on how hard the puck is pressing against the ice. That's embodied in the idea of the normal force. Normal, once again, perpendicular to the surface. And the ice is pushing up on the puck, just as gravity is trying to pull the puck down. And in fact, because there isn't any vertical motion, those two forces have to balance out. The normal force itself has to equal the weight of the puck, and that's just mg. So that's the first detail to make note of. Now, calculate the friction force itself. We know that the friction force is proportional to the normal force in magnitude. The friction force equals the mu, the coefficient of kinetic friction, not writing a subscript in this case, times the normal force. And then we know that we can replace the normal force with mg, the weight of the puck, and plug in the values. So the mu is 0.25, the m 1.2 kilograms, g, our old friend, 9.8 meters per second squared. So we get the strength of the friction force is about 2.94 newtons. Next, well, let's take a look at net force equals mass times acceleration, Newton's second law. Here the motion is in the horizontal, so we really just need the net force x component equals the mass times the acceleration x component. But in the horizontal, the only force acting on the puck is the friction force, and it's acting to the left. If F represents a positive number, the strength of the force, then the net force as a component is going to be the negative of F, and that's going to equal the mass times the acceleration. Plugging in some values, we have negative 2.94 equals 1.2 times that acceleration, a sub x. Solve for the acceleration. A sub x is about negative 2.45 meters per second squared. Now we have the initial speed of the object, 23 meters per second. We know it's going to slow down and stop, so the final will be 0 meters per second. And we have the acceleration. That sounds an awful lot like a Chapter 2 problem. Let's go to the next slide and analyze the motion of the puck itself. Here, we'll let the puck start out on the left, move to the right, and its initial velocity, 23 meters per second, positive 23, the way the coordinate system is set up. And it will slide across the ice until it stops. So its final speed is going to be 0 meters per second, if you will. And the distance that it goes is going to be the same as the displacement, the delta x, and that's what we're actually going to solve for in this problem. And since the object's moving to the right but slowing down, must be the acceleration is to the left, and that certainly agrees with the result from the previous slide, finding that acceleration being a negative number. Well, in our constant acceleration equations, the third equation is a good match for this problem. Final velocity squared equals the initial velocity squared plus 2 times the constant acceleration times the displacement. We have our values to plug in, and we can solve for the delta x. Ends up being about 108.0 meters. And that is our first friction problem.